Here we'll introduce secants and tangents for circles. But first, take a look at this circle here. Of these line segments, which is a chord? And if you'd like to review chords, click down here instead. Right, this segment is a chord because a chord connects 2 points on a circle. Now a secant is a line that passes through 2 points on a circle. So if we extend this line segment into a line going on forever in both directions, it passes through the circle at this point and also at this point. So that's 2 points, meaning this line is a secant. Next, take a look at these 4 lines. Which 2 of these are secants? Exactly, these 2 lines are secants. This one passes through the circle at 2 points, and this one also passes through at 2 points. Now, a tangent is a line that passes through exactly 1 point on a circle. That might not sound possible, but take a look at these 4 lines. One of them is a tangent line to this circle. Which one is it? Precisely, this line is a tangent touching the circle at a single point, this one over here. Now there's an interesting property of tangent lines to circles. Let's draw in a radius that also goes to this point where the tangent line touches the circle. What do you notice about the radius and the tangent line? If you're not sure, just click down here. Exactly. The radius and tangent line are perpendicular, making a right or 90-degree angle. And this is always true. For any point on a circle, the radius to that point and the tangent line through that point are always perpendicular. Let's move these lines around so you can really see this is true. So to summarize, a chord is a line segment between 2 points on a circle, a secant is a line passing through 2 points on a circle, and a tangent is a line passing through just 1 point on a circle. And as you've seen, tangent lines are always perpendicular to radii that go to the same point. Let's start with a circle, and suppose you have a point outside of it. Which of these line segments are tangents between this point and the circle? Exactly, these are the 2 tangents. Now which one appears to be longer? The one up here, the one down here, or do they appear to have the same length? Precisely, so it looks like these 2 tangents have the same length. Let's see if we can prove that this is always true, no matter what circle or point you pick. First, let's draw in the radius that goes to this point up here and the radius going to this point down here. Take a look at this angle up here between the radius and its tangent line. What's the measure of this angle? Excellent. This angle measures 90 degrees. Radii and their tangents are always perpendicular and intersect to form right angles. And so the angle between this radius and its tangent also measures 90 degrees. Now let's draw one more line segment between the center of the circle and our point out here. Now of all the line segments we've drawn, which one is the longest? Right, this line segment in the middle is the longest. Let's label it with a single hash. And the 2 radii over here are congruent to each other, meaning they have the same length, so let's mark them both with 2 hashes. You might notice that we now have 2 triangles here. This upper triangle, which will move over here, and this other triangle, which will move over here. If you look carefully at these 2 triangles, you'll notice they're congruent. Going around both triangles, they have matching longer sides, then matching shorter sides, and then matching 90-degree angles. So, by which postulate are these 2 triangles congruent? Right, so these 2 triangles are congruent by SSA, longer side, shorter side, angle. So because these 2 triangles are congruent, that means their corresponding sides must also be congruent. So then which side of the bottom triangle must be congruent to this side of the top triangle? So this side up here must be congruent to this side over here, and let's label them both with 3 hashes. Let's put our congruent triangles back into our diagram. This side with 3 hashes is the upper tangent, and this side with 3 hashes is the lower tangent. And we've just proven that they have the same length. So using the longer side, shorter side angle postulate, we've proven that from any point outside a circle, the 2 tangents to that circle are always congruent to each other. Great, so let's try using this fact to solve a problem. Here's right triangle ABC, and let's draw a circle that's tangent to all 3 sides of the triangle. In other words, each side of the triangle is tangent to the circle, touching it at exactly 1 point. Let's draw in the radii to all 3 sides, and suppose this circle has radius 1. Suppose also that this line segment here has length 3, and this line segment down here has length 2. Try using this information and what you know about tangents to determine the side lengths of triangle ABC. And if you get stuck, click down here. Nicely done. The radius of this circle is 1, so this length is also 1. If you look at this shape in the bottom left with right angles and equal side lengths, it's a square, so these segments here also have length 1. And because this tangent has length 2, this tangent must also have length 2. And this tangent has length 3. So as you found, triangle ABC has side lengths of 3, 4, and 5. You can use this fact about tangents to prove a whole bunch of other facts about tangents and circles. Here's an example. Suppose you have 2 circles, and here are 2 line segments that are tangent to both circles. Now it looks like these 2 segments have the same length, but how can we prove it? Well, let's extend both line segments until they intersect. If you just look at these 2 segments here, they're tangents from this point to the smaller circle. So then, according to this rule, they must have the same length. And if we look at these longer segments, they're both tangents from this point to the larger circle, so they must also have the same length. And that means these 2 segments must have the same length, since they're both equal to the long tangent minus the short tangent. There are plenty of facts you can prove about tangents and circles. See what else you can discover. Here we'll introduce circumscribed angles, which are angles between 2 tangent lines. But first, let's make sure you remember what a tangent is. Here's a circle and a few lines that pass through it. Which of these lines is a tangent? Exactly, this line is tangent to the circle because it touches the circle at exactly 1 point. Let's extend this line a little bit. And let's draw a second tangent line over here. This angle over here between the 2 tangent lines is an example of a circumscribed angle. Let's also highlight the arc that's between the 2 points where the angle hits the circle. As you'll discover, there's a special relationship between circumscribed angles and their arcs. First, what would you say is the approximate measure of this arc? Remember, the measure of an arc is defined as the measure of its central angle. So in other words, what's the approximate measure of this central angle over here? Great! So it turns out that this arc measures precisely 125 degrees because that's the measure of its central angle. Next, take a look at these 2 purple angles between the radii and tangent lines. What's the measure of each one of these angles? Exactly, these are both 90-degree or right angles. Radii and tangent lines that meet at the same point always form right angles. So next, take a look at this quadrilateral, which we've colored yellow. So far, you know 3 of the angles in this quadrilateral, and the circumscribed angle is the 4th angle in the quadrilateral. But before we solve for this angle, do you remember what the 4 angles in every quadrilateral always add up to? If not, click down here to review. Right, every quadrilateral's 4 angles always add up to 360 degrees. So given these 3 angles, try figuring out the measure of the circumscribed angle. Excellent! So this angle measures 55 degrees. Now you might have noticed that the circumscribed angle and the arc are supplementary. In other words, the circumscribed angle and the arc's central angle add up to exactly 180 degrees. Let's see if we can prove that this is true in general, that circumscribed angles and their arcs are always supplementary to each other. Suppose we said this arc had measure x, which means its central angle also has measure x. Again, these two angles between the radii and tangents are right angles or 90 degrees. So again, using the fact that the angles in this quadrilateral add up to 360 degrees, what's the measure of the circumscribed angle in terms of x? Nicely done. And so you've just proven that if an arc has measure x, then its circumscribed angle measures 180 degrees minus x. In other words, they're supplementary. They always add up to 180 degrees. Now it's time for you to make your own circumscribed angle. Try dragging this yellow point around the circle. The circumscribed angle, meaning this angle between the two tangent lines to the circle, is shown in green. The central angle for the arc is shown in blue. And no matter where you draw your circumscribed angle, you can see up here that it's always supplementary to the measure of the arc. So after you've played with this interactive for a bit, try answering this question. What's the measure of a circumscribed angle whose arc measures 110 degrees? So once again, you've proven in this lesson that a circumscribed angle, meaning an angle between two tangents to a circle, is always supplementary to its arc. Try using this fact to solve one final problem. Here's a circle, and let's draw a tangent line down here. At each of these endpoints, let's draw in another tangent line. And let's also draw in a radius to each of the tangents. Suppose this angle down here measures 60 degrees, and this angle over here measures 70 degrees. See if you can figure out the measure of this angle up here. There are a few different ways to solve this problem, but if you get stuck, click over here and we'll work through one of the ways. Excellent work! One way to solve this is to see that this central angle is supplementary to this circumscribed angle, so it's 120 degrees, and this angle is supplementary to the 70-degree angle, so it's 110 degrees. Since these three angles in the middle add up to 360, that means this angle measures 130 degrees. So again, nicely done. Also, you might have noticed that 130 happens to be the sum of the 60 and 70 degree angles down here. Perhaps you can prove that an angle like this is always the sum of the two circumscribed angles. But in any event, the big takeaway from this lesson is that a circumscribed angle, like this one, is always supplementary to its arc.